In this presentation, we want to see how to take a set of data, find the frequencies for that data, and then make a plot of those frequencies and compare that plot to the normal distribution. We are going to make a probability distribution, which looks an awful lot like a histogram. So to get a sort of sneak peek of where we're headed, let's make a quick histogram. Remember, highlight the data, go to Insert, Chart, Statistical Chart, Histogram, and then format the x-axis and choose a bin width of 0.1. Many distributions are close to a normal distribution, also known as a Gaussian distribution, also known as a bell curve. And so we are going to remake this histogram in a somewhat more tedious procedure, but it's going to allow us a very direct and visual comparison with the normal distribution. The normal distribution has two parameters, the mean and the standard deviation, where the peak should be centered and how spread out it should be. So we will find these quantities, the mean and standard deviation, for this flywing data, so that when we plot a normal distribution corresponding to this data, we will have the necessary parameters. The frequency is the number of times a result occurred. So the flywing had a length of 3.9 twice. But we're going to convert the frequencies into percentages. So we are going to divide by the number of data points. And so to that end, we are calculating the number of data points using Excel's count function. Recall that when making a histogram, that the data is broken up into bins and that the bins span the range of the data. So toward this end, we must know the range of the data. And so we are calculating the minimum and maximum of the data. Before we had Excel just sort of choose bins for us, but now we're sort of making them for ourselves. And a bin is a little sort of sub-range, but here we are just telling you the sort of highest number in the range. And to sort of deal with the issue of is 3.6 in the bin, we make the bin go up a little bit higher. So that's why it's like 3.60001, so that there's just that little bit of extra to ensure that the 3.6 data point ends up in that first of our bin. Then our next question is sort of, what is this width of the bins? How spread out are they? And there's no exact rule here. Remember, that's a parameter that Excel lets you play with. What's the width of the bins, or how many bins are there? So there's no fast rule. You want to have bins that don't have, you don't want everything in one bin, and you don't want too many empty bins. Now this data sort of came to us nice. It sort of went up by 0.1s, and there were a number of points once we get into the middle of the data at each. So like 4.1, you can see, had a number of data points with that value. So it seems sort of a natural choice here, but this is part of the artistry of making these things, of picking the bin width. We want to give a warning that the next step in our procedure is going to be using an array formula. So a non-array formula, a regular Excel formula, you pick a certain individual cell, you enter a formula in it, then you click enter and enter that formula, and it calculates the quantity for one cell. And then we may fill that formula down a column or across a row, but it's doing the calculation sort of cell by cell. An array formula is different. The calculation is done for a whole set of cells simultaneously, and so it takes a little more care. First, you have to highlight a large region, so sort of the whole region that the answer is going to go into before you start. So you don't enter the formula in a single cell, you enter the formula in a group of cells. And then you don't enter it in the normal way just by hitting enter on the keyboard, but you must hit Ctrl-Shift and Enter together. Also, later on, when you've successfully entered such a formula, if you end up in one of these with your cursor in one of these cells and you make a motion that Excel thinks is an edit function, then you are trying to edit one part of what is a whole group of answers that belong together and are treated as a unit, and Excel is going to complain and it's going to become very fussy. And you just want to get out, and so that's usually by the escape button. So previously we established what I called the range values, which are sort of the upper limit of all of the bins. And now I want to find the frequency, the number of data points that occur in each bin, and that is going to be the frequency formula, which is one of these array formulas. So we highlight the entire region. It's an array formula. We have to do it all at once. Highlight the entire region next to the range values where the frequencies are going to occur, and then enter the formula equal the keyword formula name frequency, and then we are using the data, which was A2 colon A101, that's the data, comma C2 colon C21, those are the bin values, and then close the parenthesis, and then Control Shift, and with Control and Shift still down, then hit Enter, and you have entered an array formula. So here we see the result that the frequency of the 3.60001 was 1. There was one data point in that bin, the 3.6 data bin. There was one data point in the 3.7 data bin. 2 data points in the 3.8, and 2 in the 3.9, and 4 in the 4, etc. Okay. Note that the numbers go up, that the frequency numbers go up and then down. One of the standard errors that people make in this formula, the numbers just keep going up, so that might be a sign that you made a mistake. Also note in this equation that when we've entered it, then Excel has put these curly brackets around it to indicate that it is an array formula that was entered. You do not type those curly brackets. They are introduced by Excel because it was entered as an array formula. So the formula as normal, as you type it, starts with equal, and then it's Excel that does the curly brackets. So don't look at this picture here and think that you type the curly brackets. You do not. Here we make a quick XY scatter graph. We're not going to format it. We're not going to design it. We just want to have a quick look at what's happening so far. And so the X's will be the bin range, and the Y-axis will be the frequencies. And that's what we have right here. Recall that we want to compare this to a normal distribution or bell curve. And so we're showing here the formula for a bell curve. Remember that we said the bell curve, the normal distribution, has 2 parameters. So here in the equation shown, the function shown, the y is the variable. It's the thing that changes. And then we have 2 parameters. The mu, that thing that looks a bit like a U, and that is the average, the mean. And then the sigma, that little thing that looks a bit like an O, that's the standard deviation. These are the 2 standard parameters that define a normal distribution, where it will be peaked, the mean, and how spread out it will be from that peak, the standard deviation. As we said, the normal distribution is a very standard, important distribution in statistics, and so Excel has a normal distribution built in, so you can get it by saying equal NORM.DIST. Then comes first the variable, which again we are using the bin values or range values for. And then next come the 2 standard parameters, the mean and the standard deviation, and that was in B2 and B4 as we calculated some time ago, and we're using $sign because we're going to copy this formula down. So the normal distribution that we're entering here is just a normal Excel function, not like the frequencies, which are an array formula. So this is going to be copied down, and so we're using the $signs to, when we copy it down, to keep those things fixed, because it's the mean for the entire distribution. It's the standard deviation for the entire distribution. And then the false, that fourth argument. Remember, the arguments are the things in the parentheses. The last one is an argument saying false. And this is going to be that we're not going to sort of be accumulating all the results, but just talk about what's in that one bin. And that's what the false means. If you look at columns D and E, you see we're not quite ready for a direct comparison. The numbers look vastly different, although they do have the same pattern. They peak at the same point. So our first step is to turn the frequencies that are in column D into percentages, and this will be closer to the sort of probability distribution that is the normal distribution. So instead of saying that the value 4.2 occurred 7 times with a sample size of 100, we want to say that 4.2 occurred 7% of the time, or 0.07. And so toward that end, we are dividing the frequencies in column D by the count, which was in B6, and the count is the same for, of course, all of the whole set, so we're dividing by $6. So we're entering that in column F and copying down the formula. And so now in F we will have percentages instead of frequencies. The normal distribution is a continuous distribution, but we're not really working with a continuum here. We've been working with these bins. So the number 3.6 is really standing in for all the numbers between 3.6 up to, but not including 3.7. So to do this, we're going to take our normal distribution in column E and multiply it by the bin width. This is the way in which we will allow the single point at 3.6 to really sort of stand for all the numbers from 3.6 up to 3.7. Another way of thinking of it, to say that the bin width has something to do with it in this comparison, let's look at the frequencies we had in column D. There were about 20 different frequencies here, and they were largest values were 10 there in the middle. And we had a bin width of 0.1. What if we had chosen a bin width of 0.2? Then there would have been sort of half as many frequencies, but we would expect those frequencies to be sort of twice the value. So that's where this bin width plays its role, and the way we're dealing with it in the normal distribution is to take the point and multiply it by the bin width. So take the values in E and multiply them by our bin width, which was 0.01. So we are finally ready for this direct comparison. So we're highlighting our X values are going to be those bin values back in column C. And then we're going to, our Y's, we're going to have two sets of Y's, the normal distribution and those percentages. And so that's columns F and G. So remember, when you are highlighting cells that are not next to each other, you use Control. So you can highlight column C and then hold down Control and highlight columns F and G, and then let go of Control once you have everything highlighted, and then go on to make an XY scatter graph. I chose a quick layout number 1 to get title, axis labels, and so on. And I changed those axis labels. The X was the length of the housefly wing, the Y was probability, and I entered some title that says where the source of data was. I formatted the X-axis and changed the minimum X value. Next, I want to control what the legend says, and toward that end, I'm going to right-click on a data point and choose Select Data from the context-sensitive menu. I highlighted the first series, which was the data, and clicked on Edit, and then in the Edit Series dialog box, I entered the series name. Then I repeated for Series 2, which was the normal distribution. And here we see the result with the series names now appearing in the legend on the right. Now the second series, the red, is the normal distribution as a mathematical function. So I would like to present that as a solid line. So toward that end, I right-click on one of the red points and choose Format Data Series. And then then in the Format Data Series pane that pulls out on the right, I am going to edit the line and choose it to be a solid line, and I can also change its color if I would like. And also toward this end of noting that it's a mathematical function, I want to take away the individual markers for the points, and so I move over to the editing, formatting the marker, and I'm going to choose no marker, so no big dots, just sort of this solid red line. And so here's our result. The blue is the data, and we turned it from frequencies into percentages or probabilities, if you will, and then the red is the normal distribution with the appropriate mean and standard deviation, and we see that it's a fairly reasonable comparison, that the data does seem to be very normally distributed. It is a bell curve. It is Gaussian. So we've just seen a very visual comparison of the data distribution to the normal distribution. But recall we also had individual measures, quantities derived from the data that also compared it to normal distribution. These were the skewness and the kurtosis, the Excel formulas SKEW and KURT. So next, get the SKEW and KURT for the fly-wing data. Recall that the skewness told us whether the distribution was symmetric, the same on both sides around the peak. And so if the skewness was it can be positive or negative depending on which way it is skewed, which way it sort of leans. But if the skewness, if the absolute value of the skewness, if you will, is less than 1/2, then we can say it's pretty close to symmetric. If the absolute value of the skewness is between 1/2 and 1, we might say that it's moderately skewed. And if the absolute value of the skewness is greater than 1, we would say that it was highly skewed. The kurtosis measures how the data falls off from the central peak. Excel's version of kurtosis is designed to be 0 for the normal distribution. Then a kurtosis less than 0 says that the central peak is sort of broad, but then there's not much in the tails. The tails are sort of short and thin, whereas a kurtosis of greater than 0 says that the central peak is sort of sharp, but then there are longer, bigger tails.